Welcome students to the ManaTv live telecast program. I am Dr.R.V.S.PRASAD from PRR and VS Government Degree College, Vidavalluru, Nellore district. Today we are going to discuss the linear programming problem in three parts. First, we will discuss the formulation of LPP. The next, its graphical solution. The next, the simplex method, that is the solution of, in fact, this graphical solution and the simplex method are the solution methods of linear programming problem. Before discussing all these topics, let me tell you the preamble of this linear programming problem. Linear programming problem is a part of operations research, a beautiful subject which was started in 1947 during the Second World War. Yes, during the Second World War. In fact, the England army during that Second World War, having limited resources like army, budget and ammunition also, then the problem came how to utilize these limited resources in a most effective manner. The team of scientists sat together and thought about this problem. Then the subject operations research. This operation means any job. Research, an effective procedure to perform that particular job is named as research. So, the operations research is an effective procedure to utilize the limited resources in a most effective manner. After the World War, this subject, operations research subject, entered several real life problems like transport, medicine and in other different subjects. Recently, I went through a paper in an international journal. The techniques of operations research, particularly the linear programming problem, had been effectively used in signaling in traffic control particularly. I wondered how they formulated that problem. They found the solution of that particular problem. Anyhow, the conclusion of that particular paper is, after effectively applying this solution, the traffic problem is solved to some extent. And William Sati, of course, the operations research have different definitions. Sati, a statistician, I like his definition basically. He told that the subject operations research find bad answers for the problems, otherwise they are worse. డెఫినేషన్ నేను బాగా ఇష్టపడతాను. ఇక్కడ సాటి చెప్పిన ఆ అంశంలో ఆపరేషన్స్ రీసెర్చ్ అద్భుతాలు చేస్తుందని అయితే చెప్పలా. వర్స్ సిచ్యుయేషన్స్ మనకు ప్రాబ్లమ్ సొల్యూషన్స్ ఎదురైతే, సొల్యూషన్స్ మనం ఏదన్నా ఒకటి అప్లై చేసినప్పుడు సిచ్యుయేషన్ వర్స్ అయితే దానికంటే బెటర్ చేయొచ్చు అని చెప్పాడు. చాలా హంబుల్గా, చాలా ఆనెస్ట్గా దీన్ని చెప్పారు. అండ్ హ్యావింగ్ డిఫరెంట్ dimensions of operations research, its modeling, and there are different models in war. All this you have already discussed in your classrooms. Now the present topic is the linear programming problem. The last word is problem. It's a problem naturally. This middle term is programming, a versatile word in computer science. Programming, a systematic procedure. Programming means a systematic procedure. The first one is linear. You know the linear equations where the variables of a particular equation in first degree. If it is in second degree, we will call it as a non-linear equation second, that is more than 1 degree, non-linear. But our discussion now is confined only for linearity. So in this linear programming problem, at the beginning, we will discuss with formulation of LPP, how to formulate the problem. ఇక్కడ తమాషా ఏంటంటే ఒక రియల్ లైఫ్ సిచ్యుయేషన్ని వీఆర్ కన్వర్టింగ్ ఇన్ టు ఏ ప్రాబ్లం ఇట్ ఈజ్ ఎ రియల్ లైఫ్ సిచ్యుయేషన్. ఏ సిచ్యుయేషన్ కూడా మనం ప్రాబ్లంలోకి మార్చుకొని ఆ ప్రాబ్లంకు సొల్యూషన్ మెథడ్స్ కనుక్కుండే ప్రయత్నాలు దీంట్లో మనం చేస్తాం. దెన్ వాట్ ఈస్ ది డెఫినేషన్ ఆఫ్ దిస్ లీనియర్ ప్రోగ్రామింగ్ ప్రాబ్లం? ఇట్ ఈస్ ది టెక్నిక్ ఆఫ్ ఆప్టిమైజింగ్. ఎ బ్యూటిఫుల్ వర్డ్, ఆప్టిమైజింగ్ means either maximization or minimization. Suppose the real life situation is about a profit problem, it is maximization. Or if it is with respect to the production, the cost, then it is the minimization problem. If it is a transportation problem, we have to minimize the transportation cost. So a common word either for maximization or for minimization is simply optimization. So LPP is an optimization, either a maximization or minimization problem of a linear function of variables. This will call it as an objective function. Objective function means mana laksham endi, mana objective endi, maximize చేయడమా, మినిమైజ్ చేయడమా. ఈ మ్యాక్సిమైజేషన్, మినిమైజేషన్ కొన్ని కండిషన్స్కి లోబడి ఉంటుంది. ఇప్పుడు మీకు మేము లెసన్స్ చెప్తాం, మాకు కండిషన్, వీఆర్ నౌ రన్నింగ్ ఇన్ సెమిస్టర్ సిస్టమ్. అవర్ ఆబ్జెక్టివ్ ఈస్ టు కంప్లీట్ ది సిలబస్ విత్ ఇన్ ది స్టిపులేటెడ్ టైమ్. దట్ ఈస్ అవర్ ఆబ్జెక్టివ్ ఆఫ్ ది టీచర్. ఆటోమేటికలీ స్టూడెంట్స్ హ్యావ్ దేర్ ఓన్ ఆబ్జెక్టివ్స్. దే వాంట్ టు మినిమైజ్ ది సబ్జెక్ట్ టు బీ స్టడీడ్ and later they should get more marks in the examination. That is their objective. Of course, we will try to optimize, we will try to get either maximization or minimization. The students try to minimize the syllabus, the teacher tries to maximize. So there are conditions to explain a problem. Basically, the conditions are named as either constraints or simply they are restrictions. Specifically to say objective function, it is a linear relationship reflecting the objective of an operation. Operation means a job, whatever the job may be. A linear relationship reflecting the objective of an operation. In most situations, the objective is either maximization or minimization. Maximization in case of profit or minimization in case of production cost. And the LP model formulation, it consists of, in the LP model formulation, there are two major parts. The first one is the decision variable. A decision variable is an unknown quantity representing the decision that needs to be made. Decision means how many items are to be produced. If it is a product mix problem, our objective is to find how many items for model A and how many items for model B are to be produced. It is the quantity the model needs to be determined. How much? Quantity means how much. Suppose a manufacturing concern is manufacturing two models A and B. The problem is how many items of model A and how many items of model B are to be produced. And basing on some restrictions, which we will call them as constraints. After all, constraint is a linear relationship representing the restriction on decision making. Everything has its own restriction. In different problems, we have our own restriction. In making our family budget, there is restriction. There are limited resources. These limited resources we are particularly mentioning as restriction. So basing on this type of problem environment, what are the various steps involved in the formulation of a linear programming problem? It is a very simple procedure, my dear students. First, we have to define the objective. That is, either we have to maximize the situation, the objective function, or to minimize the objective function. A combined word for both is optimization. And later, we have to define the decision variables. As I already mentioned, how many items of model A and how many items of model B are to be produced. They are the decision variables. Then we have to write the mathematical function for the objective. Either maximize like this, maximize Z equal to, or minimize the production cost, like that. Then we have to write down the different constraints. The constraints may be either greater than or equal to inequality, or simply equality, or they may be less than type inequality. My dear students, the less than type inequality in operations research, particularly in linear programming problem, is named as type 1 inequality, and the greater than or equal to inequality is named as type 2 inequality. So, for convenience, problem convenience, we will divide them into two types. The first one is type 1 inequality, less than or equal to, and the second one is greater than or equal to inequality. This is under type 2 inequality. So, basing on this discussion, let us go through a problem environment. A problem is visible before you. A firm proposes to purchase some fans and sewing machines. It has only 5,760 rupees to invest and a space for 20 items. A fan costs rupees 360 and a sewing machine rupees 240. And the profit expected from a fan is rupees 22 and a sewing machine is rupees 18. The objective is to maximize the profit. And this we have to formulate as an LPP. If you go through this problem, there are two items he has to purchase. The first one is fans and the second one is sewing machines. The available investment is only 5,760 rupees. To purchase a fan, we have to invest 360 rupees, and for a sewing machine, it is 240 rupees. But there is a space constraint. ఎన్నంటే అనుకుని మనం పెట్టుకోవడానికి కుదరదు. We have to use a constraint that there is a space limitation, both combining these fans and sewing machines. We can invent only 20 items. This situation we have to formulate as an LPP. First, I am writing a decision table here, my dear students. As I already, in the problem environment, there are two articles. The first one is fan, the second one is sewing machine. And how many fans are to be purchased? It is X1. How many sewing machines are to be purchased? It is X2. And the maximum investment, available investment is rupees 5,760. So, to purchase a fan, we have to invest 360 rupees. To purchase a sewing machine, we have to invest 240 rupees. And space, only one fan, one sewing machine. And profit is also mentioned. On a fan, we are going to get a profit of rupees 22. And on a sewing machine, we are going to get a profit of rupees 18. So, after giving the problem, going through the problem, we have to prepare like this a decision table which we can easily formulate the LPP. And after converting it, our objective is maximizing the profit. Hence, our objective function is maximize, that is the profit, Z equal to, profit for fan is 22 rupees, profit on sewing machine is 18 rupees. And we decided to purchase X1 fans and X2 sewing machines. Hence, the objective function is maximize Z equal to 22X1 and 18X2. Then what are the restrictions? The first restriction is on investment. For every fan, we have to use 360 rupees. For every sewing machine, 240 rupees. So the first constraint is on investment is 360x1 and 240x2 is less than or equal to, because the maximum available investment is only rupees 5,760 rupees. Hence, the first constraint is 360x1 plus 240x2 is less than or equal to 5,760 rupees. And the second constraint is, what is that? It is the constraint on the space. Okay. So, for one fan and one sewing machine and only 28, there is a space only to adjust 20 items. So, it is the space constraint. The second one is x1 plus x2 is less than or equal to 20, and automatically this is a product mix problem. The problem is to decide how many fans and how many sewing machines. Both numbers should not be negative. Somebody says purchase -5 fans. It is ridiculous. So, a non-negativity constraint includes here x1 should be greater than or equal to 0, as well as x2 is also greater than or equal to 0. So, this is the first constraint, that is the constraint on investment, and this is the second constraint, the constraint on space, and this is the non-negativity constraint. This combination, the objective function, the constraints, as well as the non-negativity constraint constitute a linear programming problem. Okay? And let us go to another example also. It is also a product mix problem, of course. A person requires 10, 12 and 12 units of chemicals. There are 3 chemicals, A, B and C respectively, for his garden. A liquid product contains 5, 2 and 1 units of A, and B, C respectively per jar. 3 chemicals A, B, C respectively per jar. And a dry product contains 1, 2 and 4 units of A, B, C per carton. The liquid product sells for rupees 3 per jar and the dry product sells rupees 2 per carton. The objective is to minimize the cost, because the person has to purchase either this liquid product or dry product. The objective is to minimize the cost and to meet the requirements. This problem situation we have to formulate as an LPP. As I mentioned earlier, first we have to make a decision table. There are 2 products here. The first one is liquid, the second one is dry. Suppose x1 items of liquid product, x2 items of dry product, the person want to purchase. And these are the minimum requirements on the chemical A, and these are the minimum requirement that garden requires, particularly A 5 units, B 2 units, C 1 unit, and in a dry product A 1 unit, B 2 units and C 4 units. And the cost for this liquid product is rupees 3 production cost, and dry is rupees 2. And minimum requirements for A, there should be 10 units, chemical A 10 units, and B 12 units, and C 12 units it is also. And obviously our objective is to minimize the cost, hence minimize Z equal to 3x1 plus 2x2 our objective function. And we have 3 constraints here. In the earlier problem we have only 2 constraints. Here we have 3 constraints. Subject to the constraints, 5x1 plus x2, as in the decision table mentioned, is greater than or equal to 10, because the minimum requirement is 10 units. The second constraint is 2x1 plus 2x2 is greater than or equal to 12. And the third constraint is x1 plus 4x2 is greater than or equal to 12, and including this non-negativity constraint x1, x2, x1 should be greater than or equal to 0 and x2 is greater than or equal to 0. So, my dear students, before formulating the LPP, please convert the given problem environment into a decision table, which helps you to make formulation easy. Or After formulation of the LPP, linear programming problem, now let us think about its solution methods. There are different solution methods for solving the linear programming problems. Basically, the operations research problem can be solved either in analytical method or in iterative method or using Monte Carlo technique. And in the previous section, we tried to formulate a linear programming problem, a structure of consisting of an objective function, the constraints along with a non-negativity constraint, of course. And let us first discuss its graphical solution, how to solve an LPP using graphical method. And it is a very simple, it is also a very simple procedure. That is, the graphical procedure has its own restriction, of course. The restriction is, it can the graphical solution for an LP problem can be applied only when the LPP consists of only two decision variables. If there are more than two decision variables, we will go for simplex method, which we will discuss later, of course. Suppose the given LPP has only two decision variables, that is the objective function, constraints with the two decision variables, and a non-negativity constraint. Then the first step says that plot each constraint as an equation and then decide which side the line is feasible. The first step, we have to prati constraint to, as this is a linear programming, every constraint we have to convert it as strict equality, which is converted to a line, it is a straight line. This we have to put in a graph. The next one is we have to find the feasible region, we will discuss, and find the coordinates of the corner or extreme points of the feasible region, and substitute the corner points in the coordinates of the objective function. And the last one is choose the optimal solution, optimization. Either you have to maximize the objective function or you have to minimize the objective function. And we have to know two terms particularly. The first one is the extreme points. The corner points of the bounded region are called extreme points. The corner or vertices of the feasible region are referred to as the extreme points. An optimal solution, we have to, an optimal solution to an LP problem can be found only at extreme points. This is a most useful point why this graphical solution became most popular. In fact, a problem has several solutions. Suppose our objective is to maximize the LPP. We have to write down the solution, we have to find the solution, we have to put it in the objective function and check whether this solution is optimizing the problem, that is either maximizing or minimizing. But in graphical solution, basically the optimum solution exists at the corner points of the feasible region. This is particularly a benefit through graphical solution. When looking to the optimal solution, it would not evaluate all feasible solution points, as I pointed earlier. I have to consider only the extreme points of the feasible region, so that this graphical method became most popular. Having identified the feasible region for the problem, we now search for the optimal solution, which will be the point in the feasible region with the largest in the case of maximization and the smallest in the case of minimization. And to find the optimal solution, we need to evaluate the objective function at each one of the corner points of the feasible region. And what is the feasible region? The feasible region for two variable linear programming problem can be non-existent, ఉండకపోవచ్చు feasible region, or at a single point, ఒకే పాయింట్ దగ్గర ఉండొచ్చు, or a line, or a polygon, or an unbounded area also, having three different dimensions. It can be either non-existent, ఉండకపోవచ్చు, or at a single point, or it may be a line, or a polygon, or an unbounded area also. Any linear programming falls one of these three categories. It can be infeasible, it can have a unique optimal solution or alternate optimal solutions, or has an objective function that can be increased without bound. That is, the objective can be increased. Mana korikalaga, mana korikalaga kuda limitations undavu. Sometimes our requirements will be unbounded, like that. A feasible region may be unbounded, and yet there may be optimal solutions. This may be common in minimization problem, of course, but sometimes it is possible in maximization problem. So the procedure has only 3 steps. That is, we have to convert the inequalities of the constraint inequalities as strict equalities. Then we have to plot each constraint on the graph paper, find out the feasible region, identify the corner points, and substitute these corner points in the objective function and check where the function is optimized, at which point the function is optimized, so that you will get the required optimum solution. And I have mentioned a maximization problem first. The problem is maximum z equal to 5x1 plus 7x2. The objective function is maximization, and there are 3 constraints here. The first one is x1 less than or equal to 6, 2x1 plus 3x2 less than or equal to 19, and x1 plus x2 less than or equal to 8. And there is a non-negativity constraint also. Both the variables x1 and x2 should be greater than or equal to 0. So this is the objective function, and there are 3 constraints which are type 1 inequalities, and the next one is the non-negativity constraint. And now the first constraint is x1 less than or equal to 6. Okay, take x1 equal to 6, as I already mentioned. Convert these inequalities as strict equalities. If x1 equal to 6, this x1 equal to 6 line is parallel to y-axis like this. Yet on x-axis the point is 6, 0. So plot this line first on the graph. First constraint is graphed here, and the second constraint is 2x1 plus 3x2 is 19 is equal to 19. Of course, there is less than or equal to. We have to convert it to equality. 2x1 plus 3x2 is equal to 19. And if put x2 equal to 0, 2x1 equal to 19, and x1 equal to 19 by 2, that is 9 1 by 2. The point on x-axis is 9 1 by 2 0, and put to x2 equal to 0, 2x1 equal to 19, and x1 equal, and put x1 equal to 0, 3x2 equal to 19, x2 equal to 19 by 3. The point on y-axis is 0 6 1 by 3. And this is the third constraint, x1 plus x2 is less than or equal to 8. This is the constraint, and equality is x1 plus x2 is equal to 8, and the points are 8 0 on x-axis and 0 8 on y-axis. So the 3 constraints had been graphed, and this is a combined constraint graph, and this is the first constraint, this is the second one, and this is the third one. And dear students, did you observe the common region, and here, 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 and here also? This is the common region. Okay, as I mentioned, this is the feasible region, and this is the combined constraint graph, and this is the common feasible region. And the common feasible region, the corner points are, the first point is 0 0, and the second point is 6 0, and the third point is 6 2, and the fourth point is 5 3, and the fifth point is 0 19 by 3. This is the feasible region. And what is the next step, dear students? We have to substitute these corner points in the given objective function. You see, the objective function, you substitute the first point 0 0, the outcome z is 0, and for the second point 6 0, the outcome is 30. The next point is 6 2, the outcome is 44, and the next point is 5 3, fourth point, it is the objective is 46, and for 0 19 by 3, we will get the value of the objective function as 44.33. Did you observe all these objectives? And the maximum value is 46. Hence, the solution corresponding to which maximized, which is the reason to get this maximum value 46 is this x1 equal to 5 and x2 equal to 3. That is the solution. So, here I marked it the optimal solution. Since the largest set is 46, the optimal solution is x1 equal to 5 and x2 equal to 3. And let us go for a minimization problem now. The problem is minimize z equal to 5x1 plus 2x2, and the constraints are 2x1 plus 5x2 less than greater than or equal to 10, and the next one is 4x1 minus x2 greater than or equal to 12. There is a third constraint also, x1 plus x2 greater than or equal to 4, and non-negativity constraint also exists. So, this problem in this problem environment, the problem is minimizing the z and having 3 constraints, and all they are type 2 inequality, type 2 inequalities greater than or equal to inequalities, and consisting of a non-negativity constraints. And here I am explaining in a wider manner, of course. And for the first constraint, to put x1 equal to 0, x2 equal to 2, then the connecting points of the first constraint are 5, 0 and 0, 2. And for the second constraint, we observe, my dear students, when x2 equal to 0, x1 equal to 3, and the point is obviously it lies here, but setting x1 equal to 0, x2 equal to minus 12, and we are graphing all the constraints in the first quadrant to satisfy the non-negativity constraint. So, x2 equal to minus 12 does not exist, and 5, 8, and the feasible region falls above the line, of course. And when x1 equal to 0, and the connecting points are 4, 0 and 0, 4, and then we have to find the intersection points, and for the first and second constraints, the intersection point is this is one is 16 by 5, the other is 4 by 5, and now by getting all these constraints to graphed, this is the common feasible region, and having only 3 corner points. One is at 5, 0, and the second one is 10 by 3, 2 by 3, and the next one is 16 by 5 and 4 by 5. And then these corner points have been substituted in the given objective function, and at 16 by 5 and 4 by 5, the value of z is 88 by 5, and at 10 by 3, 2 by 3, objective is 18, and at 5, 0, the objective is 25. Among them, the minimum value is 88 by 5. Hence, the solution of this LPP, which is used, which is solved through graphical method, is x1 equal to 16 by 5 and x2 equal to 4 by 5. And of course, we will face different special cases, and sometimes the given LPP has alternate optimum solutions, my dear students, and there is a solution. Maybe another solution may optimize and another solution may get optimized. There will be multiple optimal solutions, and this case, in this case, you see, this is the objective function here. Maximize z equal to 3x1 minus x2. These are the constraints, and z1 and here, and then z2 went to another optimal solution, and z3 went to another optimal solution. So, sometimes we will get some LPPs with multiple optimal solutions, and sometimes we may get infeasible problem also. Suppose this is the problem, 2x1 plus 6x2 maximize, that is the objective function, maximize z equal to, the constraints are 4x1 plus 3x2 less than or equal to 2x1 plus x2 greater than or equal to 8. One is type 1 inequality and the other is type 2 inequality, and automatically non-negativity also constraints. And here you see the infeasibility. As I already mentioned, in a product mix problem, we have to determine how many items of model A and how many items of model B are to be produced. ఎంత రిడిక్యులస్గా ఉంటుందండి, x1 మైనస్ 5 x2 మైనస్ 3 అని చెప్పడం. సో దాన్ని మనం ఇన్ఫీజిబిలిటీ అని అంటాం. ఇక్కడ చూడండి, రెండు ఇందాక చెప్పిన కన్స్ట్రైంట్స్ గ్రాఫ్లో మనం ప్లాట్ చేస్తే ఇవి ఫస్ట్ క్వాడ్రంట్లో ఎక్కడ ఇంటర్సెక్ట్ చేసుకోవాలా, ఈ 2 కన్స్ట్రైంట్స్కి కామన్ ఫీజిబుల్ రీజియన్ రాలేదు, గమనించారా? కామన్ ఫీజిబుల్ రీజన్ రాలే ఇక్కడ. అందువల్ల ఈ ప్రాబ్లంకి ఈఎల్పిపికి ఒక ఫీజిబుల్ సొల్యూషన్ లేదు అని చెప్పి మనం అంటాం. దిస్ ఈజ్ అనదర్ కేస్. అండ్ ది నెక్స్ట్ వన్ ఈజ్ అన్బౌండెడ్ ప్రాబ్లం. This is a very beautiful solution. There is a problem environment here, solve graphically and for the optimal solution, and the problem, the objective is maximization. Of course, there are two constraints, and one is x1 plus x2 is greater than or equal to 5. This is the second constraint, including the non-negativity constraint, and this is, you see, both constraints are graphed here. And there is no common feasible region because both are type 2 inequalities. It is going above the line, the common region. It is unbounded, having no bounds. This is another case, my dear students. So, you have to remember only 3 points, particularly in graphical solution, and it has its own restriction. The restriction is, what is the basic restriction? An LPP having 2 variables only can be solved graphically. సొల్యూషన్ వస్తుందని గ్యారంటీ అయితే లేదు. ఎందుకు లేదు అని అంటే నేను స్పెషల్ కేసెస్ మీకు స్పెషల్గా చూపించాను, గమనించారా? ఒకటేమో అన్బౌండెడ్ కేస్, ఒకటేమో ఇన్ఫీజిబుల్ సొల్యూషన్. If it is a product mix problem, if somebody asks us how many items of model A and how many items of model B are to be produced, how ridiculous it appears. You produce -3 items for model 1 and -5 items for model 1, and it's infeasible. And sometimes multiple optimal solutions. ఒక సొల్యూషన్ మనం అనుకున్నాం అనుకోండి, మనకి అనిపిస్తుంది ఏమో దీనికంటే బెటర్ సొల్యూషన్ ఉందేమో, దీనికంటే బెటర్ సొల్యూషన్ ఉందేమో కాదు, ఉంటాయి కొన్ని సందర్భాల్లో. వీటన్నిటిని కూడా మనం ఈ గ్రాఫికల్ సొల్యూషన్లో డిస్కస్ చేసుకున్నాం. కాబట్టి జాగ్రత్తగా ఈ గ్రాఫికల్ సొల్యూషన్ క్లస్టర్ పాయింట్, ఎగ్జామినేషన్ పాయింట్ ఆఫ్ వ్యూలో ఖచ్చితంగా ఒక సమ్ గ్రాఫికల్ సొల్యూషన్ మీద ఉంటుంది, మై డియర్ స్టూడెంట్స్. సో ప్రాక్టీస్ ఆల్ డిఫరెంట్ మోడల్స్ ఇన్ ది గ్రాఫ్. Suppose an LPP has more than 2 variables. We cannot apply the graphical method. Graphical method is limited only for 2 variables. And for that, there is another method processed by G. Dancing in 1947, which has only 3 major parts. There will be a trial basic feasible solution for the constraint equations, and then testing whether the solution is optimal or not. And the next one is improving the first trial solution by a set of rules. And then among these 3, then what is the general form of linear programming problem? Optimize, that is either to maximize or to minimize z equal to c1x1 plus c2x2 plus so on plus cnxn, subject to the constraints a11 x1 plus a12 x2 plus so on a1n x1. It may be less than or equal to, means type 1, equal to or greater than or equal to inequalities b1, and a21 x1, a22 x2 and so on a2n xn is less than or equal to or greater than or equal to b2, so on am1 x1, like that. This is the mth constraint. So the general form can here this general LPP consists of there are n decision variables and m constraints, and the notations are xj, the jth column, it is the decision variable column, and b, this is the constraint levels values, and the next one is the objective quotients, objective function quotients, objective maximize z or minimize z, there will be the quotients, and the next one is the quotients in the constraints and variables. And I already mentioned it can be the constraints may be with type 1 inequality or with type 2 inequality. we have to make in solving the simplex method as strict equalities. To convert the inequality constraints as strict equalities, we require two types of variables. The first one is slack variable, the next one is surplus variable. Slack variable, this we will use for type 1 inequality. Suppose the inequality is 3x1 plus x2 less than or equal to 1. We have to use one slack variable, say s, s1 equal to 7. And the second, say the inequality is type 2 inequality. We have to subtract some quantity. It is the subtracted quantity is named as the surplus variable. It is also mentioned with s. The variable with minus sign is surplus variable. The variable with plus sign is slack variable. Then what is the standard form of LPP? The first one is we have to convert all the inequalities as strict equalities, and the right side element of the equalities with plus, and that is if there is a minus sign, you simply multiply with minus, and the objective function should be of maximization form, and it can be also written as in the matrix form as maximize z equal to c x transpose, where x equal to x1 x2 so on, and the slack are surplus variables, and it is the constraint subject to the constraints ax is equal to b after converting them into strict equalities, and b greater than or equal to 0, and a here a is, this is the quotient matrix here, this is the variable matrix, this is the quotient matrix of the objective function, this is value levels of different constraints. And then what are the definitions? What is a solution? Very simple అండి. సొల్యూషన్ అంటే మన ఆబ్జెక్టివ్ ఫంక్షన్ని మనకి ఇచ్చిన కన్స్ట్రెంట్స్ అన్నిటినీ సాటిస్ఫై చేసే ఆ సెట్ని మనం ఏమంటాం అంటే సొల్యూషన్ అంటాం. దెన్ వాట్ ఈజ్ ఎ ఫీజిబుల్ సొల్యూషన్? ఫీజిబుల్ మీన్స్ మన ప్రోడక్ట్ ఇందాక మనం చెప్పుకున్నాం కదా, మిక్స్ ప్రోడక్ట్ మిక్స్ ప్రాబ్లం వగైరా వగైరా అని, వాటిల్లో ఏ డెసిషన్ వేరియబుల్ కూడా నెగిటివ్ కాకపోతే దాన్ని మనం ఫీజిబుల్ సొల్యూషన్ అంటే మనం నమ్మదగ్గ సొల్యూషన్ అని మనం చెప్పొచ్చు. And then basic solution, and there is word basic feasible solution, a solution which is basic and also which is feasible. Then what are the various steps in the simplex algorithm? First you convert the given LPP into its standard form, as I already mentioned earlier, and construct the simplex table, and then compute the net evaluations Zj minus Cj. My dear students, sometimes people are evaluating Cj minus Zj, no problem. You calculate either Zj minus Cj or Cj minus Zj, which we will call them as net evaluations. If all Zj minus Cj are greater than or equal to 0, and the optimal solution is obtained in the first table itself, it is not so, we have to go to the next steps. Then we have to select two vectors. That is the first iteration, we have to in the net, among the net evaluations we have to select, because net evaluations Zj minus Cj, the entering vector most negative and the outgoing vector the most positive of theta, and this process is to be continued till the end. And to explain this algorithm, I mentioned a problem, I considered a problem here. The objective is maximize z equal to 3x1 plus x2. The inequalities are of course type 1, x1 plus x2 less than or equal to 4, x1 minus x2 less than or equal to 2, and this is the non-negativity constraint. Okay. Then as I mentioned in the algorithm here, I used two slack variables, one is s1 and the other is s2, and both appeared in objective function also with 0 quotients. So this is the standard form of the LPP, and the initial simplex table, and having different columns Cj, these are the quotient in the objective quotients of the objective function. This is the quotient of x1 of the, this is quotient of x2, this is the quotient of s1, s2, the slack variables 0, and cost basis, variable basis, value basis, these are the original variables and these are the slack variables, and put the original variables in the objective function as 0, will get s1 equal to 0, s2 equal to 0, and these are the values of b. You do the net evaluations Zj, will get naturally, that is 1 into 0 plus 1 into 0, 1 into 0 and minus 1 into 0, like that add, and you will get the net evaluations as Zj minus Cj, minus 3, minus 2, 0, 0. Among them the most negative is minus 3, and the corresponding x1 variable enters the basis. Then we have to decide which variable leaves the basis. For this we have to calculate theta b by the entering vector x1. We got two values 2, and I mean 4 and 2, and 2 is the minimum theta, this out goes. So, in the first iteration table, x1 enters the basis and s2 leaves, and 1 is the point of intersection of these two are, it is called the key element. And for the, then we have to go for the second iteration, of course, and for that we have to calculate these new, and these are my notations only, my dear students, and the simplex table consists of different rows, and for the second iteration, for the second simplex table, what is the second row? New R2 and new R1. You perform the calculations like this, and this is the first iteration, the simplex table, of course, that is the second simplex table, of course, first iteration, because earlier we call it as the initial simplex table. It is the first iteration, and these are the cost values, and here x1 entered the basis in the place of s2, that is the previous table, and its cost quotient is 2, like this, and we calculated zj values, and later we calculated zj minus cj like this. It is -1, -4, and among them most negative is -4, and so corresponding variable is x2. So, x2 enters the basis, and least theta is 1. Dear students, here put a dash, because here it is negative. Least positive theta we have to select. So, x2 enters the basis and s1 leaves, and 2 is the key element. These are the required calculations for it to enter the table, and this is the second iteration table. You have the net evaluations zj minus cj 0, 0, 5 by 2, 1 by 2. Have you observed, my dear students, all the net evaluations became non-negative, means positive. It means we attained the optimum solution. Here I wrote, since all zj minus cj are non-negative, the optimum solution is obtained, and the solution of this is x1 equal to 3 and x2 equal to 2, and maximum z is equal to 11. And dear students, this is the process of using simplex method in solving the LPP problems, and it is the best method. మీకు ఒక మాట చెప్తాను, మై డియర్ స్టూడెంట్స్, డాన్జింగ్ ఈ ప్రొసీజర్ ఇంట్రడ్యూస్ చేసిన తర్వాత ఇంత గొప్ప ప్రొసీజరు 107 years నుంచి వేరే ప్రొసీజర్ పుట్టలేదంటే మీరు నమ్మాలా. అంత అద్భుతమైన ఈ సింప్లెక్స్ ప్రొసీజర్. ఆఫ్ కోర్స్ దేర్ ఆర్ సెవరల్ డైమెన్షన్స్. వీ డిస్కస్డ్ ఓన్లీ విత్ టైప్ 1 ఇన్ఈక్వాలిటీస్. దేర్ ఆర్ టైప్ 2 ఇన్ఈక్వాలిటీస్ ఆల్సో. Type 2 inequalities means greater than or equal to inequalities. There we have to use surplus variables with minus sign. Then artificial variables. We'll discuss all these things, of course, in the next discussion. And thank you very much for the team, for ManaTv team, for giving me this wonderful opportunity. I hope all the students as well as teachers may be benefited, should benefit through my talk. Thank you, one and all.